Hello everybody. In this video we're going to continue to look at integration by substitution. Here we have a recap on the method or the technique of integration by substitution. So what we want to do here is evaluate an integral whose integrand is of the form of a composition of functions f of g of x multiplied by the derivative of the inner function, so multiplied by g prime of x. And what we're going to do is that we're going to rewrite that integral to be an integral with respect to u instead of with respect to x. And we can do that by letting u equal to the inner function, g of x. When we do that, then we can see that we can rewrite the integral in the form of the integral of f of u du. And that hopefully is an integral that we can evaluate then immediately or directly. And we have tried to set it up to achieve that. How we achieve it is by looking at the relationship between du and dx, the relationship between u and x through the derivative du dx. And that allows us to rewrite the integral as we want to. So we look at some general rules then that we can derive really from this method of substitution. So the indefinite integral of sine of kx dx for any constant k is given by minus 1 over k times cos of kx plus c. The indefinite integral of cos of kx with respect to x is given by 1 over k times sine kx plus c. And you can show these just using the method of substitution by letting u equal to the inner function kx each time. Similarly, the integral of the exponential of kx dx is given by 1 over k times e to the kx. And we have seen examples like this earlier. So for instance, if k is 3, then the integral of sine kx or sine 3x dx is given by minus 1 over 3 times cos of 3x plus c. And this is very similar to an example that we worked through in detail in the last video. And similarly, the exponential of minus 5x is minus 1 over 5 times the exponential of minus 5x plus a constant. Just following these general rules. So let's look at some other examples then, ones where the functions maybe look more involved. So suppose we wanted to evaluate 8x times cos of 4x squared plus 3, and we're evaluating that integral with respect to x. So again, what we have here is a composition of functions, cos of 4x squared plus 3. So the inner function here is 4x squared plus 3, and that's what we let u equal to. Then we look at the relationship between u and x by finding the derivative, du dx. And we see that we can write du as 8x times dx. And that is going to work for us because here in our original integrand, we have 8x and dx. So we can substitute into the original integral. So we're substituting 4x squared plus 3, the inner function, by u, and the 8x times dx by du. And that allows us to write the integral very simply as the integral of cos of u du. And we know the integral of cosine is sine of the same variable, and we'd add an arbitrary constant. And here we've just rewritten the integral in terms of the final answer in terms of x. So here what we really got was cos of u plus a constant, and we just substituted 4x squared plus 3 back in instead of u. Now, you can always check your answer by reversing the process again, differentiating. So if we just take our answer, sine of 4x squared plus 3 plus a constant, and differentiate it, we'd need to use the chain rule, but we'd see what we get is cos of 4x squared plus 3 multiplied by the derivative of the inner function, the derivative of 4x squared plus 3, which is 8x, and then the derivative of the constant is 0. And tidying up, we see that this is equal to our original integrand, what we were trying to integrate previously. So we've seen by reversing the process by differentiating, we've checked our answer and seen it to be correct. As a second example then, suppose we wanted to evaluate the integral of cos cubed of x times sine of x with respect to x. So remember the cos cubed of x here, that means cos of x all cubed. So that's where we have our composition. That's where we have our composition. It's here, it's the function cos of x within a cubic function. So we're going to let u equal to the inner function cos of x. Then find du dx, which is minus sine of x. And that allows us to write sine x times dx as minus du. So there's a relationship between dx and du, and we use that when we're rewriting our integral, or re-expressing our integral. So we take the original integral, cos cubed of x times sine of x dx, try and write it as an integral in terms of u. So the cos of x all cubed is going to be replaced by u cubed, and the sine x dx is going to be replaced by minus 1 times du. Integrating u cubed with respect to u, we get u to the power 4 divided by 4 plus a constant. And then we write our answer in terms of x. So we replace the u by cos of x again. So u to the power 4 becomes cos of x to the power of 4, or cos 4 of x. That's our final answer. That's the value of the integral, but we can check our answer again by reversing the process differentiating. So we take our answer and differentiate. To do that, we would have to use the chain rule. But when we do that, we see that what we get is the integrand we started with. So we know then that our answer is correct. Our answer to the integral, our value that we found for the integral, is correct. Sometimes it's not quite as simple as that. So sometimes our integral isn't in exactly the form that we want it to be, to use integration by substitution. But that can often be rectified by just adjusting the integral by a constant. So we can multiply by a constant and divide by that constant again. And that won't change the value of the integral, but it does allow us to put it in the form that we want. So I'll show you an example so you can see how that would work. So for instance, suppose we want to evaluate the integral of the square root of 4x minus 1 with respect to x. So remember, the square root is the same as to the power of a half. So here we have a composition of functions with 4x minus 1 inside another function to the power of a half. But usually for our integral that we're going to evaluate by substitution, in the integrand we have a composition of functions multiplied by the derivative of the inner function. Here the derivative of the inner function, or the derivative of 4x minus 1 with respect to x would be 4. But we don't have a multiplier of 4, a factor of 4 within our integral here. But what we can do is we can put one in and then balance it by also dividing by 4, taking it out, and that would allow us to use the method of integration by substitution as we want to. So we just start as we normally do. Let u equal to the inner function, 4x minus 1. Find du dx. Du dx is 4, so we can write du as 4 times dx. So we take our original integral. Now to substitute the dx by du, we need to have 4 times dx there, but we don't. So what we do is we put in a 4. So we add in a 4, a factor of 4 as a multiplier, but then we also have to divide by 4 as well. We can do that outside. We can do that with a constant outside the integral. So what we have here, this expression on the right hand side is exactly equal to the expression on the left hand side, but it's in a form that allows us to apply the method of substitution more easily. So now we can write this as a quarter times the integral of u to the power of half du, and we can integrate or evaluate that integral with respect to u quite easily. So we add 1 to the power, we get u to the power of 3 over 2, divide by that same power, 3 over 2, and we add our arbitrary constant to integration. And then we just tidy up. So tidying up the constants, the coefficients of u to the 3 over 2, we get 1 over 6. And finally, we substitute back in what u is in terms of x. And that's our final answer. So as a second example, just to make sure that you're following that approach, suppose we were to look at this integral here. So again, we have an integrand where there's a product, and one of the factors in the product is composition. So the first factor here, we have y to the 4 plus 4y squared plus 1 all squared. That's composition of functions, and that's multiplied by another factor. So we'll let u equal to the inner function as before and find du dy. Find the derivative, the relationship between u and our original variable of integration. That's 4y cubed plus 8y. So du is equal to 4y cubed plus 8y times dy. That's not exactly, this factor here isn't exactly what we have in the integrand, but it is very close. We see if we were to multiply our 2y cubed, 2y cubed plus 4y by 2, then we would get 4y cubed plus 8y. So we can try that. So we're going to take the original integral, add in a factor of 2, but make sure we balance that by also dividing by 2. And now the integrand is in the form that we want. We can replace it very easily by u squared du as before. Then we evaluate that integral, get u cubed over 3. It's multiplied by half, and we're adding an arbitrary constant of integration. And finally, we rewrite our answer in terms of the original variable y. So to recap here, we've just been looking at more examples where we use the technique of integration by substitution. And in some cases, it can be applied exactly as is set out, but in other cases, we need to manipulate the integrand a little bit so that it'll work. And in the examples that we've looked at here, we're just multiplying and dividing by a constant, by the same constant, so we don't change the overall value or the overall integral we're trying to evaluate, but we can write it in the form we want. We'll leave it there. Thanks for listening.